In this video lecture again we will see some more examples on Fourier series. In our last video lecture we have seen the two examples where the period of the function is 2L and the interval was 0 to 2L, and now here the interval is 2L for L constant, but the period is 2L but the interval is minus L to L. And on this we will see our third example, which is find Fourier series expansion for the given function fx is equal to 0 when minus 5 less than x less than 0 and is equal to 3 when 0 less than x less than 5. That is, the function is defined in the intervals. In the intervals minus 5 to 0 and 0 to 5. Our starting step is to talk about L. So see, here the interval is minus 5 to 5, and therefore we compare this with minus L to L, and we will get L is equal to 5, and therefore we assume the required Fourier series expansion B fx is equal to a0 by 2 plus summation n takes values from 1 to infinity an cos of n pi x divided by 5 plus summation n takes values from 1 to infinity bn into sine of n pi x divided by 5. Give number 1 because this is the answer. Only thing is to find the values of the Fourier constants a0, an, bn. So a0 is given by 1 by 5 integral minus 5 to 5 fx dx, but minus 5 to 5 is divided into two subintervals, that is minus 5 to 0 and 0 to 5, and therefore we take a0 is equal to 1 upon L is 5, 1 upon 5 integral minus 5 to 0 into 0 dx. Why? Because in minus 5 to 0 the function is defined as 0 plus 1 by 5 integral 0 to 5 into 3 dx. Why? Because in 0 to 5 the value of the function is 3. So the first integration is already 0 because fx is 0. So only thing is to evaluate 1 upon 5 integral 0 to 5 3 dx. So its value comes out to be 3. So that a0 is 3. Next, an is again 1 by 5 integral minus 5 to 0 fx is 0 because in minus 5 to 0 fx is 0. So 0 into cos of n pi x divided by 5 dx plus 1 upon 5 integral 0 to 5 3 into cos of n pi x divided by 5 dx. See, here also the interval minus 5 to 5 is divided into minus 5 to 0 and 0 to 5, and accordingly we have taken the values of the function. That is, in minus 5 to 0 the value of the function is 0, and in 0 to 5 the value of the function fx is 3, and therefore we write an is equal to 3 by 5. The first integration is 0 and second integration is integration of cos of n pi x by 5 is sine of n pi x divided by 5 into 5 by n pi. The limits are 0 and 5, which comes out to be 0 because sine n pi is 0 and sine 0 is 0. Next, bn is 1 upon 5, exactly on the same way, 1 upon 5 integral minus 5 to 0 0 into sine of n pi x divided by 5 dx plus 1 upon 5 integral 0 to 5 3 into sine of n pi x divided by 5 dx. Here also the first integration is 0 and second integration is c. Integration of sine is minus cos, and therefore at the start we write bn is equal to minus 3 by 5 into bracket cos of n pi x divided by 5 into 5 by n pi. The limits are 0 and 5. But cos of n pi is minus 1 raised to n and cos 0 is 1, and therefore we if we substitute the limits, finally we will get the value of bn as bn equal to 3 by n pi into bracket 1 minus 1 raised to n, and putting these values of a0, an and bn, we will get the required Fourier series expansion of the given function fx as 3 by 2 plus summation n takes values from 1 to infinity 3 by n pi into 1 minus 1 raised to n into sine of n pi x divided by 5. See, here cos term will not appear because an is 0. If we put the value of n and expand this series, we finally obtain the Fourier series expansion as fx is equal to 3 by 2 plus 6 by 5. Why 6? Because the value of 1 minus 1 raised to n is equal to 2 when n is odd, and therefore 2 will common in each term. We take it out and multiply it with 3 so that we will get 6. So again I will repeat the last step. Fx is equal to 3 by 2 plus 6 by 5 into bracket n is 1 upon 1 sine of pi x by 5. N is 2, the value is 0, so no need to write that term, plus 1 by 3, n is 3, 1 by 3 sine of 3 pi x divided by 5 plus 1 by 5 sine of 5 pi x divided by 5 plus and so on. Again I will focus your attention on the value of 1 minus 1 raised to n is equal to 2 when n is even, and the value of 1 minus 1 raised to n is equal to 0 when n is even, is equal to 2 when n is odd, and 1 minus 1 raised to n is equal to 0 when n is even, and therefore we obtain the required Fourier series expansion as given in the last step.
Okay.
The fourth example is find the Fourier series expansion for fx is equal to 0 when x lying between minus 2 and minus 1 is equal to k when x lying between minus 1 and 1 is equal to 0 when x lying between 1 and 2. So exactly as in example 3, we write our first step as the answer, that is fx is equal to a0 by 2 plus summation an cos n pi x by 2 plus summation bn sin n pi x by 2. Why 2? Because the interval is minus 2 to 2, and if we compare this with minus L to L, we will get L is equal to 2. Exactly on the same line, a0 is 1 upon L, 1 upon 2, only minus 1 to 1 k dx remains, because in minus 2 to minus 1 and in 1 to 2 the value of the function is 0, and therefore a0 is 1 upon 2 integral minus 1 to 1 k dx, that is kx by 2, the limits are minus 1 1 is equal to k. an is equal to 1 upon 2 integral, again same line, 1 upon 2 integral minus 1 to 1 k into cos of n pi x divided by 2 dx. In minus 2 to minus 1 and in 1 to 2 the values of the function is 0, and therefore these integrals will not appear, only one will appear, and that we have written here. If we integrate this, we will get k by 2 integration of cos is sine of n pi x by 2 into 2 by n pi. The limits are minus 1 and 1, and since sine of n pi by 2 is sine of n pi by 2 minus sine of n pi by 2 we will get, and therefore an finally we obtain as 2k by n pi into sine of n pi by 2. Lastly, bn, the last Fourier constant, bn is 1 upon 2 integral minus 1 to 1 k into sine of n pi x divided by 2. So integration of sine is minus cos, that we have written minus k by 2 cos of n pi x by 2 into 2 by n pi, and the limits are minus 1 to 1, and it is equal to 0 because cos of n pi by 2 is 0, and therefore the required Fourier series expansion from equation 1 will be fx is equal to k by 2 plus summation n takes values from 1 to infinity 2k by n pi sine of n pi by 2 cos of n pi x divided by 2. So here bn is 0, therefore the last term will not appear. So that is equal to k by 2 plus 2k by pi into bracket 1 into cos of kx by 2 plus 1 upon 3 cos of 3 pi x divided by 2, then plus 1 upon 5 cos of 5 pi x divided by 2, and so on. I will correct this. Here it will be minus because sine of 3 pi by 2 is minus 1. Sine of pi by 2 is 1. Sine of 3 pi by 2 is minus 1. Sine of 5 pi by 2 is again plus 1. And therefore the final answer we will get like this. So thank you. Be safe. Be connected. Stay home. Thanks again.